Hi, my name is Facundo, and in this video I'm going to show you how to use the software OpenFiberSeg to extract the pores and fibers in a tomographic scan of a fiber reinforced polymer composite. So what we have here is the data as it comes out of the scanner after reconstruction. And if we open it in ParaView, just playing with the opacity of the color map, we can appreciate that there are three phases essentially. There are the pores in dark, there are the fibers in white here, and in this view it's transparent, but the matrix is also present. So essentially three phases. In this video, I'm gonna work with my colleague Doan and explain to him all the steps required to use the OpenFiberSeg software. First, we're going to do the pre-processing, in which we isolate the pores by themselves. Then we're going to use a software called Insect, created by a group in the Danish Technology University, to isolate the fibers. And once we have this fiber information, we're going to run OpenFiberSeg to do the extraction. So by that I mean to identify individual fibers in the volume. From that information, we're going to be able to produce this kind of visualization in which the individual fibers are labeled either by their deviation from the vertical or by their length, and also produce other kinds of statistical information as you can see in the paper. Okay, so this is the code version that you get directly from the GitHub. What we're going to do is start from one of the parameter sets, and we're going to make them work, like do the changes required so that it works with your data. So first, we're just going to copy one parameter set, like say for this one, peak 40. And okay, so you're on my hard drive. The way I like, if you get it from the code, you can get from the GitHub, I mean, you have all the code, and you also have the sample data that I used in the paper. And when you do it like that, you have a folder called tomographic data. And what this means is relative path. If you have a dot and then the path, so it means from where we're running this script, which is here, there's another folder with a subfolder called peak, and that's where the file is. In our case, we put it somewhere else. On my hard drive, it's actually on a different hard drive. So this is the address. So I'm going to use this address for your new case. Now this is the new parameter set that we're working on now. So the common path, it can be an absolute path or a relative path. So in this case, it's an absolute path. In Windows, it's gonna be a little different. It's gonna be C something. Usually Windows works with backslashes, but you can leave forward slashes and Python gets it. Yeah. So that should be okay. First thing, we gotta give it a case name. This can be anything, but usually I just keep the last folder so that it's easier to know what we're looking at. So instead of the previous scan name, it's going to be this, filament item. And then on top here, I need to select, like give it a new, declare this variable to what we're working on now. Comment this one. So now the scanning that's active, let's say, it's this one. So it's going to it's going to go through the list. It's going to compare, and then it finds, okay, this one, it's a match, so it gets into here. If you don't have any match, like if you make a typo or something, and you run it, it's going to make an error very soon because nothing's going to be defined. None of these parameters are defined because it flew by. So here, you can also check if it goes in by using breakpoints. Like if I put a breakpoint in here, the red dot is a breakpoint, and then I start it. It's gonna crash on the. It's gonna stop where it finds the first breakpoint. So then you know it entered this this case. Okay, so now we're in. This is the path where we have our data. I usually put the raw data inside a folder named like this, and this is how it's hard coded inside the code. So it's not gonna work if it's not spelled like this.
Okay.
And you point to the folder above. And inside here, depending on what system you use or exactly what options you use to generate your pictures, your slices, there's going to be a different naming convention. For our system, there's always 4 numbers and some prefix. So I made the code so that it finds the prefix automatically, so you won't have to worry about that. Also, it used to be that we had to look at how many pixels there were and input it manually, but now I made it so you can just tell it. If you tell it the pixel range is none, then it's going to automatically use all the pixels. The pixel range can be useful if you have like a scan. I'm going to open it with GIMP so that we can look at it a bit more clearly, because they're often going to be very dark, these images.
Mm-hmm.
Yeah, this doesn't matter. So with GIMP we can do something like it's not exactly a histogram equalization, but it's just the levels. So say you wanted to work only on the top right or something, then you can find the pixel values and just crop it to that region and work only on that. So that's a way to do it. But usually if you want your entire scan, it's not worth worrying about the pixel values exactly. So you're gonna, if you leave it at none, it's gonna use all the values. One thing though, I didn't, this is not automatic. You're gonna have to tell it how many pictures there are. So in this case, if you just go to the very end, like press N on my keyboard, there's 980, same as the previous data set. So I put this here. You can also decide you only want, like we're going to do now when we're going to, here we're going to process all the slices. There could be a reason why you want only like from 200 to 500 or something. So you would write it here and that would crop it to those. But also when we're looking for parameters, it's going to be, we can't plot, because it's going to run through an entire function, say the histogram equalization, for instance, and it has to run through the entire list of files of slices. So if there's 900, it's going to make 900 figures. So that doesn't work. Yep. So for this stage that we're finding parameters, I usually look for somewhere in the middle. It's not really important that it be exactly in the middle, and I leave like 4 or 5. So in this case, let's try with 4. So 401, 2, 3, 4. That's
yep.
And so now it's only going to make, it's going to process these 4
images.
Yeah.
Yep.
So for now, I left these all to true. For this is the plotting. Once you have your parameters, you need to put them back to false. So it doesn't do the figures, it just runs through the script.
Yeah. Otherwise, it's gonna plot like 900.
Yeah. Well, actually, I made a check now. So if I leave it like for many figures and I try to run it, it's gonna give you an error. These parameters will cause production of too many figures.
Ah, okay, great.
So I made a check. If there's more than 40, it doesn't run. Because if it starts and it starts generating 100 pictures, you're going to lose control of your machine.
Like
it's really annoying. So put it back to 400, 4. Okay, so now I put this all to true. This one means I do it in parallel, like I send every slice to a different CPU core, and it runs simultaneously. It goes faster that way, but it's also, you have to be aware, like there's many processes, like many threads at once. And this one, if you, like you can put it at false if you don't want to save anything, but usually I just leave it on and I remember to only consider the data that's when it's the full stack that I want. Okay, so we're gonna run it. These are we just copied these parameters from another data set, so it probably won't work first shot, but we're gonna just run it once and see what it gives us. So now all the plotting is set to true. So let's go for this one. Okay, so yeah, this is weird. Oh, actually, there's something I should have changed. Say the default parameter for the threshold,
Oh yeah.
the thresholding for finding the perimeter, try it with none first. What that'll do is that it'll use, it's called Otsu's method. It's like it's a mathematical way to divide it in like equally weighted sets. So it gives you like a starting point. Here, okay. What's interesting with this data set is that we have there's a specimen and there's a little bit outside the specimen. So for the perimeter, we'd like to not have only the black, like really the outside, but also to remove this.
Yeah.
Because if not, it might consider this part porosity, and it'll throw off our porosity estimate. So you see here, this is the histogram for the data for one of the slices, and the orange line is it's what the Otsu's method gives us. So we're going to bring it a bit upwards. What that means really is that we have this picture, and there's values from 0 to 255, and we're going to tell it at what value, at what number do we separate it from black to white. So it's like a binary mapping. And what we want, like if you look in the bottom of my screen on the left, there's a number between brackets. I don't know if you see it, it changes like a single number. Like now it's 38, 37, 38. That's the value when I'm pointing my cursor. So you can get an estimate that way. Like outside is 0. Now if I'm inside the empty zone, it's 36, 37. And then there's almost always a lighter region.
Yeah.
At the perimeter. That's 23. Anyway, we'll try numbers a bit at random until we find something that's satisfactory. So you see, in the terminal, it gives you an estimate of what the Otsu's method found. So it was too low for 19. It was this orange line. So we're gonna bring it to, I don't know, 30 and see what it gives us. So I stop it. I run it again. Okay, this is still giving black for the, I want to, the only thing that'd be black would be inside the specimen.
Yeah, otherwise it's gonna, that region also will be porosity, right?
Yeah, it'll probably become porosity once we finish the scan. So, stopping, gonna bring it up a bit more. Like at one point it becomes really sensitive, so let's try 34. So this is a value between 0 and 255. Okay, so now it's starting to be a little better, but I still think we can go one step further. The next step after this is to find the perimeter. So you see what it gives us. What it labels green is what the script thinks is the perimeter. So we're still not getting this dark region. So a bit more, 38. Okay, this is probably going to work because you see the part outside is white, and it's not gonna and the edge. The next step is the canny edge detection. So from this image, the thresholded image, it's going to find the edges, like the strong edges, and then it's going to enclose it, like find a close contour, and that the outside of that will be the perimeter. So what will probably happen is that these big bubbles will also be considered outside. People are laughing in the office. Okay, so I'm going to close all these figures and it'll go to the next step. Yeah, it's still a little bit. Okay, you see what's happening here? There's on the outside here, there's all these little red lines, this is what the canny detection is finding. So this is kind of like a speckle pattern. This is due to noise. So what we're going to do is that we're going to increase the smoothing value for the canny. So we got these three parameters for the perimeter.
Okay.
It's so there's low and high. This is like the canny. Essentially, it does it finds the gradients in the picture, and then whichever pixel is above the high value, it's going to keep it. And whichever pixel is between high and low and is adjacent to a pixel that's already been flagged, it's going to keep it too. And that way you can avoid noise a bit. And the sigma is how much you first it convolves it with a Gaussian function, so it's a smoothing function essentially. So we're going to increase this.
So those value always we're gonna in our case do some trial and error method to find the optimum value.
Yes, there's it's not an enormous range of possible values.
Yeah.
But there's always a you need to tune them a little bit. Oh yes, I didn't like now this is already a whole lot better. You see, just changing the sigma value, that means the smoothing is a lot better. It's a bit stronger, and it got rid of all the noise, and now the perimeter is pretty much what we want. It's a bit of a shame that these pores are now considered perimeter, like they're outside the sample, but in this method it can be avoided. There's other ways to do it, but I'll show you that later maybe. Okay, so now we're done with we don't need to keep making these the thresholding figures. We don't need them anymore, and I think the perimeter is good. We can try and let me look at it again, because we didn't have to change these high and low values. Maybe we can tune it just a little bit.
So basically, for this like a few images, we adjust our perimeter values, and later we're gonna run with those values whole images, whole system.
Yes, we choose, like we have only 4 pictures for now, and we can, because assuming the scan quality is pretty much the same across the entire volume, so you don't need to check it on like 50 pictures or even more.
So it's gonna work for all like level sets.
Well, we assume that you can check it afterwards.
Yeah.
But usually, if it works for like, that's why I went for the middle too, because the first 5 or 6 sometimes they're different. But like from 50 to all the way down to the last ones, they're going to be very similar in terms of scan quality. So I'm going to show you the effects of the 2 Kearney parameters. So now you saw there was a lot of red lines. So if we increase, like say we wanted less, we would increase these 2 values. Say we increase them by a lot, so 50 and 60. It's going to be a lot more selective, and then it might not give good results at all. But I just want to explain to you what it does. Yeah, so this is still pretty decent. Okay, so you saw now that I increased the value of the Kearney, and there's a lot less of these. The perimeter is still fine because I mean it's a lot easier to find the perimeter than the pores. So let's go back to your settings. This would probably work, but I want to show you, like, if we go too far, for instance, 150 and 110. If we go too far, it'll not see enough edges, and it'll go completely inside the specimen. Yeah, you see now?
Yeah, now it's much more clear effect of the perimeter values.
Yeah. Okay, so we're gonna go back to the ones before. Okay, so we can keep this for the perimeter. The next step, it's basically the same idea, but for the pores. Now, so we're satisfied with these values for the perimeter. And now we're going to work on the pores. So we don't need to be plotting these anymore. This and this, we're done. So I'm going to put them to false. Everything else has to do with the perimeter. And now it's going to go straight to pores. So these values are the same idea, the smoothing and the high and low for the canny edge detection. We got them from another data set. So let's see what it gives us. So this is the first, like just seeing what the edge detection gives us. And the next step is going to use the, like it's going to look for the closed contours and it's going to fill them. Okay, so you remember these, the ones at the outside, they've been flagged as perimeter.
Since they are open, they will not see as endpore.
Yeah, so we can't see them, but there's a few here that we could. So we're gonna try and get those two.
Yeah.
It might not work perfectly. Okay, so now it's not finding enough, so we want to bring the criteria, the parameters down so it finds more. So let's try 180. Let's not be too aggressive because it's very sensitive.
Mm-hmm.
Okay, so here there's not really, well, you can kind of see the difference. The thing is, the contours, they have to be closed. If there's a little bit, one single pixel that's not closed, it's not going to work.
It's gonna, yeah.
So usually you have to bring it low, low, low until it starts making like false positives.
Yeah.
Yeah, you see here.
Still.
Yeah, there's still a little bit of crap. We're probably not gonna get them all. We can also try to lower the smoothing, but it's better to see how far we can get just with the canny, the low and high parameters. Yeah, you see, for some of them, like this one is really good. There's only a few things here and there missing.
Oh, yeah.
But some of them are missing. And there's another step that's... there's a step in the code that it looks for, like if there's a bubble in 3-dimension, a porosity, if there's a few slices missing, it's going to fill them. There's a way to do that. I explained it in the paper. So it might still find some of these, but we'll try and make it as good as we can from just playing with the parameters. So I keep lowering them because I'm still not getting all of them.
So basically, if it's not for this layer, it's gonna detect for the next layers, maybe like when it scans the other layers too.
Yeah, if like on the slice 300, it doesn't find one pore, but it finds it 301 and 299. It's going to be able to fill it.
Okay.
It's not going to be a problem. Okay, so we're still missing a few here. Slice 402. This might not have been the best example to show, but you can still keep trying. It's not going to be perfect every shot. There's also a way to use the machine learning from Insect to find the pores, but that's a bit more, it's not implemented as cleanly.
So
yeah, you see now it's starting to find things that are not pores. It's starting to think they are pores. I'm going to try and lower the sigma a little bit, the smoothing. I'll go back to the previous parameters. This is really sensitive, so I'm not going to move it much. very much. But like I said, it might still work if, you know, if the filling works correctly. You see, now I lowered the sigma more, and it's
yeah,
starting
lots
to
of
find a lot of things that aren't porous.
false, like the
Yeah,
false
yeah, this
pores.
is not going to be any good.
Yeah.
So it's 2.8. I can try 2.7 just to see if we can improve it. Yeah, see, now it's finding a lot of fibers. It thinks they're porous.
Yeah.
Okay, let's
So we
see.
stick with 3 or
Yeah, well,
2.8.
2.8 was okay. Yeah, 2.7, it helped a bit. I'm finding a little more. Yeah, there's still a little bit of false positives here, so I'm going to increase them back to what we found before. So for this particular data set, it'd be good to do to find the pores with insect. I can show you how to do that another time. But it'll give you a decent estimate anyway. Like it'll find 90-95% of the pores. At least it doesn't find pores where there aren't any. So you know, like if it gives you 10% porosity, you know it might be 12.
Yeah, like
it's not like a completely wrong
small
estimate.
deviation should be fine.
Yeah. Okay. So we can try and see somewhere else in the data, say at 600 to 610. Let's do a few more just to corroborate that it's really that the parameters are going to be stable across the data set. This is actually not bad. You see, the only ones that are missing are the ones touching the sides, so they're included in the perimeter. Yeah, it's pretty decent.
I think this one is, yeah, exactly.
It's missing a few
really
small ones, but you know, overall it's not bad.
They'll not affect the result that much.
Okay, so we can go one step. I think the last step is the result of the. It shows the. I call it volumetric processing. It's when I told you that it fills the slices.
Yeah.
Yeah. So this is, well, it's gonna go slice by slice. It's gonna show you the result before and after. It takes a little while, but it's gonna like the last, the final result. Okay, so these parameters are probably fine. So I won't go into these are kind of more advanced features. You probably won't need to touch those. Okay, so when you're happy with your parameters, what you do is that you tell it to run over the entire data set, and also you gotta remember to set all the plotting to false. Anyway, it's gonna give you an error if you don't.
Yeah.
So all the plotting to false, and this save data to true. So now it's gonna take a little while.
So basically we use the data set, like we have 3 data sets, the zoom center, zoom site, and with the zoom out. We just run for one of them, and we have to do this step for 3 of the data set, right?
Yes, if it's like in this case, we had, it's the same sample that we scanned in 3 different locations, and one of them was a bit zoomed out.
Yeah.
So the imaging conditions are very similar. Yeah. So you're probably going to use the same parameters again. might be a little bit of tweaking, but it's a good starting point.
Okay. So the zoom out data set for mostly porosity detection and zoom in one for usually fiber traction, right?
Yes, if you want to do the tracking of fibers, it needs to be like our fibers are about 7 to 10 microns. So the pixel dimension is going to be less than 1 micron, or you won't get enough pixels for the machine learning to see them.
Okay. Okay, great.
Okay, so now it takes a little while. You also notice that I left it at, this is with parallel handle to true. I can show you what
So it's going to use the multiple cores?
Yeah, now it just stopped, like it ran to the end of that step, so it's not showing, but it uses quite a bit of RAM. Like I have 32 out of 64 that I have, 62.5. And, well, right now it's not doing anything. Did it crash?
I hope not. I think it's completed, right?
No, it just did the first step.
Okay, okay.
It might have crashed. VS Code is not very strong for, okay, now it's continuing. What I do, I don't know how Spider will behave, but you can also run the code directly from the terminal. Like if you're either Visual Studio Code or Spider, it might not like when you have very large data types, and sometimes it does weird stuff with the parallel processing too. So if you run into strange bugs, just try to run it in the terminal, like calling for it's Python and then preprocessing the name of the script. It's basically going to do the same thing. I'm calling it again, so I'm not going to let it run because it's going to saturate my memory, but it's exactly the same as here, but it'll be more stable.
Okay.
And the output of the entire run, it creates a file called preprocessed, and it's going to put them here when it's done, in the same in the same folder that we gave it, the directory that contains the raw data. It's going to go one level above and call it preprocessed. And
we're going to use these output files the next step.
Yeah, the one for the machine learning step for Insect, we're going to have to tell it to use this path to create the dictionary. Now we have to wait for it to complete, so it's a bit of a boring video. I'm going to pause it now.
Yeah, we can pause it.
Okay, so now it's done with the processing. It gives you an estimate of the porosity here, 13.6%. And it tells you it's basically the same folder we gave it as input plus preprocessed. And it wrote these 4 files. Now we can go and look at them. So it's basically here. Whoops, I did some weird stuff. Yeah, it might not be we'll see if it's really a problem. It looks funny. You see the first layer at least. Okay, so now I'm opening it in ParaView, the volumetric TIFF file that it made. Yeah, okay, it's fine. It's just you see the very first layer, it had a bit of like the perimeter went a bit too far, but it doesn't really matter. The first and the last. So we don't need to worry about that. It's just that when I don't know how you'll see it in Windows, but here it gives you a preview, and it's the first, because a volumetric TIFF file is a stack of figures, so it gives you the first one. So you can always look manually if things make sense. Like you can open it again with ParaView and have you see I have my file here. I go to representation, volume, and then I can look at it like this. I can also play with the colors, like flip this color map. what can be useful is to have them both, like the pores and the perimeter, for instance, have them both at once, and now
Okay.
now I'm gonna separate this icon is to unlock the color map, so it's gonna use a different one for the pores, just to see if there's not something strange. Yeah, there's a bit of a bug that it doesn't like it shows you the pores even though they're behind the perimeter. This is not very reliable, but yeah, the majority of these are fine. Some of them are cut, like you see this one down here, but this might still be fine because if it starts touching the edge, then it's going to be considered perimeter.
Okay.
You remember how
Yeah. Like,
we can see them here. Some of them, you see some of these bubbles, they're actually porosity, they're not perimeter.
But still, yeah.
Yeah, so on the side it's not really that bad, but there might still be a few places where on the inside where it didn't catch the entirety of the pores, but it looks decent. Okay, so now we're gonna, and also in this file, you can open it with like a Notepad++ or something like that. It gives you the parameters that you use in case you forget or something. Like it's always good to leave a trace. If you lose your file or whatever, you didn't save it, and it gives you the porosity estimate that we had just before.
Okay.
So this is like 13.6%. Okay, so now we're gonna use Matlab for the inside part.
Yeah.
Okay, now we have to first we're gonna create a dictionary for these for this data set. Yeah. So here I don't have the automatic detection of pixels. We're gonna have to put it manually. So we're gonna create a new case.
So this Matlab file also in the Insect project and in your GitHub, right?
Yes, it's part of the public GitHub. Okay. Okay, so this one is not in the relative path. It's not here. It's somewhere else, exactly like I did it before. In here. So I'm going to give it this path. But actually, the way it's made in Matlab is that it's going to use the case name. This one, the scan name. It has to be the name of the folder.
Okay.
Because it's going to use it as a folder name, and it has to have a slash. And also in Matlab, there's a difference between a single, what's it called, quotes and
quotation mark.
Yeah, quotation. Single and double are not the same type. So here it has to be single. You see exactly like the other ones. The quotation marks. Okay, so filament ultem, that's what we have as a path here. And then pre-processed, that's the same for all of them.
Yeah.
Whoops, not here, here. Okay, so this is what I was telling you. It's gonna take, the way I find the path is that I concatenate, I have common path, scan name, and then
process file.
Name. So the scan name is already included, so it can't be in the common path.
Okay.
So I have to remove this one. If I don't, it's just going to tell me file not found.
Okay.
So there's a path mistake. So here it should be good. And also, I'm not sure how this is going to turn up in Windows though, but here what I did in the script, when it generates the volumetric TIFF file, it gives you a description. There's a little like a little bit of text that goes with it, and it tells you the dimensions, X, Y, Z dimensions.
Okay.
So X is 1004, 981. So I can use those dimensions. I'm not sure how it looks on Windows, I'm sorry. So for Windows users, basically you have to go into the view pane and ask for the details pane. And then when you look at the volumetric TIFF files, you'll have the description as well. So you can use this information instead of looking at what you specified before. It's going to be kept in storage there. 1004.
I think 2 dimension is for the TIFF file dimension, but I don't know the 3rd dimension. How gonna find it? We can find the 2 dimension.
Well, you can, yes, you can see that. And also we used it before, like the Z dimension is going to be what we use here.
So basically, yeah, like...
Yeah, it has to be, because that's how many we processed. And when we look here, it's 980.
Yeah, so, yeah, true.
Okay, so now the step the script we're working on is Insect Fiber 3D, create dictionary. So this is just about creating the dictionaries, not about processing the data. So
Okay.
we don't care how many slices we use. I can use the first 10, that's fine. Actually, I'm going to go a little bit further in because the first few are often a little bit screwed up. So say the first 10, but really we're going to work on one. Okay, let's try this. Okay, so these are the files it found, the 10 files.
Yeah.
It's fine. Now I close this first one, then it asks me, this in the Insect documentation, they have a way of determining this. Basically, it's the size of the, basically it's the size of the feature you're interested in. So in our case, it's the fibers, and they're about 10 pixels diameter. And it has to be an odd number. So, okay, so the patch size, I'm gonna leave it at 11. Usually works.
Okay.
If you have a scan that's very different, like very large fibers or very small, you can play with this a little bit. Choose a slice for training. It's gonna look for the middle one. It's usually fine. Then you have to tell it like a region of interest, like a sub region. I usually go for interactive, and then I select like a region that's typical. We already found the pores, so we don't care here. If it makes a mistake, like if it thinks that there's a fiber where it's a pore, we don't care because we already know that there's a pore there, and it's not gonna let it label a pixel as fiber if it's already a pore.
Okay.
So basically it's the fibers that we care about, so I'm going to look for regions mainly anyway. There's a lot of pores everywhere, but so you select a region and then right click on the rectangle and crop image. Once you do that, it's going to close the figure and it's going to go to the next step.
Okay.
Okay, so here you have the commands are written in the top here. Like what I usually do is I change the right hand side with W. I go to overlay. So it's going to show like the segmentation on top of the original image. So basically the feature that we are looking for, we're going to put it pink, and the rest, the background, is going to be this blue, this cyan.
Yeah.
Okay, so with the up and down arrows, you can increase or decrease this spot size.
Okay.
So basically, I give it a, like I find a region with a few fibers, First I give it a blue for everything, and then with a smaller spot size, like you want to be careful not to go beyond the true region, so it takes a little while. So you go carefully. Basically, the more effort you spend at this stage,
It's
the
gonna be much
cleaner
more
your
perfect.
yeah, the cleaner is going to be. So you can already start seeing the effect on the right hand side.
Yeah.
It's okay, but it's already we didn't spend much effort. So you see here there's the sides of the fibers are missing, and there's a little bit of bad ones around the pores.
Yes.
So we're gonna give it more fibers. Basically, we can like take feedback from the result, like around this pore, because you see the cursor is on both images.
Oh yeah.
So this here they're not fibers. So I'm gonna put this blue, and you already see this a big effect. And here also that's not a fiber. So boom, but it also removed a lot of volume inside the true fibers. So it's kind of like you remove and it removes too much, and then you add and it adds too much, or eventually you want it to converge.
Okay.
But it's usually not such a big. Like it doesn't take very long, this process. Okay, so here, for instance, we have a fiber that's partially missing. I'm gonna give it background around it, and then you see already it deleted a lot of things, because here I told it that some fibers were not fibers, so it's confused. Yeah. But then when I put it back, when I add a little bit of information, it's gonna restore it very quickly. Okay, so at this stage, it's pretty decent. We could probably go with this, but I think we can improve it. So I'm going to tell you that this region here is not fibers.
So, yeah.
Okay, now we can start just looking at the result and correcting it locally. So you see there's a little fiber here. It can be a little bit bigger. See the ones that are only partially found. Here. There's one entirely, completely missing here. Okay, now it's starting to do a few mistakes, but it's not a problem. We can deal with those later. Okay, most of the fibers are good.
Yeah, the rest is quite good.
Yeah, but it's finding stuff, it's labeling fibers where there aren't any. So this, I went back to blue, and this is not, you see already it removed the majority of the mistakes.
Yeah.
This is probably a mistake. Sometimes you're not even sure by eye too. That's one of the challenges of this kind of labeling, is that even yourself you're not sure. So the also what the tracking helps is that sometimes you're not like these fibers that are adjacent to pores. You're not sure because around the pores there's this white halo. So if there's a fiber there, it's not really that clear. But if you look at like 5 or 10 slices beyond, the fiber might have like it'll diverge a little bit. So by tracking, you can find those. You can complete some of the picture. So that's one of the strengths of the tracking thing, is that it can help you gain more precision that you would even be able by eye, because you're only on a single fiber at a time, and it would take so much work to do one against the other and go back and forth all the time. Okay, so this is starting to be acceptable. Probably improve it just a little bit.
Quite good.
Yeah, the thing is, if you try to make it like if it finds the majority fibers and also it finds the complete region, it's going to give you a better estimate of the fiber volume fraction.
Oh yeah, true.
So it's worth spending a little bit of effort here. Okay, so there's a little bit of mistake here. Whoops, it's not pink, it's blue. You can also erase. With the gray, you can erase.
Okay, that's nice.
Yeah. Like here, I'm not really sure if it's a fiber or not, but I'm gonna call it fiber because it looks a little bit bigger than just a halo. I'm gonna remove this little bit of mistake. What do you say? This looks okay.
I think it's good.
Okay, so when we're ready, we have to press the E key. I think it says so somewhere. If you close the figure, it won't let you save. Like you'll have to redo it. But if you press E for export, E, exporting variables, I don't know exactly what this is, but usually say okay.
Okay.
And then it's gonna save, it's gonna want to save the dictionary at the same place where you put the, where the data is. So usually I give it a name that's a little bit more precise, because you may want to reuse these dictionaries. Like for your other sample, it's the same specimen, it's just a different location. You can probably try this one first, so you don't have to redo a dictionary every single time.
Okay.
So we're gonna save it by that name, and then it's just gonna try and do a labeling on another one. Yeah. Boom. So this is the probability map that it sees, and it gives you the histogram, and then you have to choose a value. Usually at this stage I don't mess with it. I just use 0.5, and here is the result. It's pretty good.
Wow.
Yeah, this is it's very decent. There's a little bit of false positives, but they're very small, so they might be.
It's so small, yeah. Like it's like.
Yeah, it's almost perfect. But this is not very high filling ratio also of fibers. When there's a lot of fibers jumbled together, like touching, it's going to be harder for the machine learning. And also these scans are clean. They're high resolution. So all that helps. Okay, so that's the dictionary. Now this script is done. Now we can use these same coordinates, and we're going to bring it to actually with the scan name, to the main file. Here there's a few more.
We're going to create a new case right here.
Yeah.
Okay.
So I got to give it also on top here. I got to select the right case name, the scan name. I can give it the same as this here. I can comment this just so that we're not confused.
Okay.
Okay, so here we have to tell it what dictionary to use. So let me just copy this, and we're going to modify it accordingly. Okay, so this preprocessed file is the name of the preprocessed folder is still just preprocessed. That doesn't change. Dictionary folder. Oh, let me see how this is. I don't remember why I did it like that, but for our case, the path to the dictionary is the common path, and then whichever that one is. Because for the example one, I put them all in the. This is the data path is here, and then I had inside dictionary files, so that it was simple for the example. But for us, I'd rather keep the dictionaries along with the folder here. Okay. So I have to tell it this is the common path, and then the preprocessed path. We're gonna change it around a little bit. Dictionary folder, it's the same as this one actually. Dictionary file, this is important. It has to be the same name or it won't be able to read it. Boom.
Okay.
common path dictionary folder, dictionary file.
Dictionary file.
This should be fine. And this is the threshold that we're using. So we're going to leave it at 0.5 because the result was pretty decent before.
And we're gonna change the Z values too.
Yes, yes. We can. Yeah, remember it was 9.
Yeah, 980. Yeah.
You can always. If you forget, it's the one that we were using here.
Yep.
There's probably a way to like look at the properties or something in Windows to tell you those. You see here in the properties, I have a description field.
Okay.
I don't know how it'll be in Windows. I'm sorry, I'm a Linux person. Okay, so let's try it. Maybe it'll crash because it doesn't file the files. Oh yeah, first it's gonna start because I tell it to use as many workers as it can on this machine. Okay, so it didn't find something. Unable to open file. No, okay, I screwed up something. It's not here. It's not the right path. Oh yeah, this. Because you see, for the example, I told the script to go inside this folder and then look for the scan name and all that, but we have a different one.
Okay, so we have to.
I'm gonna call it. I'm gonna change this one, but if you want to, then if you want to use the examples, you have to remember that it was data path before.
Yeah.
This is not the most elegant way, but it's just a matter of telling it where to look for stuff. Okay, so now it's loading it, so it means it found them. It takes a little while because they're big files. They're like, these are 335, 340. Whoops. What did it not like?
Again.
Why is it still looking for data? Oh, common path. Okay, so I'm going to call this file, I'm going to call it data path. Yeah, that's a better solution. This is data path because I use the same variable data path somewhere else, and now it's all confused.
Yeah.
Okay, so leave it at that. If you, these example files, they already have their data path above here. So if you, for your cases, if you give it a new data path, it's going to overwrite the previous one, and it'll work, and you won't have to remember what you did if you want to rerun the example files.
And now it works.
Yeah, it looks like it's loading. Yeah, it's finding everything.
Same error.
Whoops. Unable to find dictionary filament ultem.mat. But it looks good. What's the matter here? Persist. Oh, I screwed up something. What's the difference?
That's weird.
Oh, there's, yeah, Dogan in the path.
Yeah.
Anyway, it's a classic mistake. But why did it? Oh, I didn't add the scan name. Yeah, it's data path scan name, I'm sorry. Yeah, because it's a different. In the example, I put all the dictionaries in the same. Now it's a little bit different. I think it's gonna work now. data path, scan name, which is this. Yeah, that's what was missing. Anyway. Okay, so once it finishes loading, first it segments an example. So it just shows you what it did. This is perfect. If you like it, you can... they're actually going to close after like 30 seconds, I think, by themselves, so you can leave it. But if you close them manually,
It's going to continue.
It's going to continue by itself, yeah.
Okay.
So at this point, you can just forget it, like leave it and it'll run its thing. Now it's... the thing is, the tracking is better when you're slicing in the same direction as the fibers. Like if the fibers are vertical and the slices are horizontal, now it finds a nice cross section for each fiber, and it can link them nicely. But if there's a fiber that's very like it's 90 degrees from this direction, like it's in the plane, it's going to find a long cross section, and it's not, the tracking is really bad for that scenario. So what I do is that I do the tracking for the main direction, and then I transpose the entire volume. So I do it from, say the first direction was Z, then I do it from the X direction, and then from the Y direction.
Y direction. So this
so
is
for
like
this,
the permutation is called permutation 1, 2, 3. Is that?
Yeah, 1, 2, 3 is for like X, Y, Z.
Yeah. Okay.
And then it's going to be 1, 3, 2, and then 3, 2, 1. Basically, because the Matlab function that does this is called permutation. I forget. Yeah, permute. Permute is the function that does it, and the vector is like the order in which you use the things. So 1, 2, 3 is the first one, and anyway, you don't really need to. You won't have to mess with it, but it's a good idea to understand at least what it's doing. So basically, there's going to be 3 folders. Yeah, it has to reach the end of the first run to generate the folders. But it's going to be one that's permutation 1, 2, 3, permutation 1, 3, 2, and 3, 2, 1. With the volumes of it's going to have the fibers, the pores, also the probability of, like the output of the machine learning part. It's the tracking going to use it for one intermediate step. But you don't need to know so many details. Just to use it anyway.
Yeah.
Okay, so we can leave it run for now and come back when it's finished.
Yeah. Okay. How many minutes can it take?
It depends on the scan. I would say for this one, maybe half an hour.
Oh, okay. So see you in half an hour.
Okay, so we're back. All the 3 permutations are finished now, and I can show you what it did. So here it called it. This is what I call the folder tag. Oh yeah, because we paused the video. We forgot to before it threw an error because I didn't declare this variable. So for people following the video, this one is it's basically the prefix for the output folder. So it's going to use processed and then the coordinates that we use. So that if you want to do several different subvolumes or something, they're not going to overwrite each other. They're going to be in separate output folders. So inside here, there's also the time. If you redo it with different parameters or whatever, they're not going to overwrite each other. So here are the 3 permutations that we talked about, X, Y, like along Z, along X, and along Y, or YX, I'm not, I don't remember. Here we're going to have basically the parameters we use, the probability. There's not really any reason to look at it, but if you ever need to find what you did, like if you lose your specification, it's going to be there. And inside each of these are the, well, basically the same ones as before, except now we have the probability of finding fibers, and the fibers. So we can already have a look at this one. See if it looks normal, if there's not something weird. For this kind of filling fraction, it's nice because we can actually see something. For some of the higher values, it's just a jumble like this. At least here across the extrusion direction, it's fairly clean. But it looks okay. There's nothing really like it's not confusing a pore for a fiber or something like that. So this is good. And the last step now, it's fairly simple. We just have to launch the tracking, the main part of the code for this folder. So we're going to use this path. And now the script is called, it's back in the Python.
Now we would go back to the Python, right? Not
yes, the only step we use in Matlab is in Seg because it was all written in Matlab to begin with and it was simple to keep it that way. Okay. But the rest of it is all Python. So here, the path that we're looking at changing is this data path. So we're going to give it another one. Now it's not a relative path like before, it's an absolute path. And it's going to look for, basically it's going to look for this function. It looks for any file that's named this way. And if it's not finished, like this is one of the last steps. Actually, I'm not even sure why that's there. It looks weird. But anyway, I'm going to show you how to launch it. Yeah, there's a bit of a mistake, but this is not a problem. I'll fix it for the... So this is the path. The first step, you can always check if the first step is good. What I usually do is that because I'm going to be plotting just to run a quick check, I don't want to run them in parallel because it's going to take too much memory and it's going to make I just want to make one file, the first slice, and see if it's good. And this is usually the plot that's interesting. You can look at what the other ones do, but they're more technical. This one is kind of more like a story. So I set this one to true, this one to false. You don't have to do this, but it's just a bit like at least you'll know if everything is normal before you launch the entire extraction. That might take like 12 hours or something, depending on your scan. For this scan, the filling fraction is not so high, so it might finish in less, like in 8 hours, but sometimes it takes more. Like I've seen scans take like days. Okay, so basically there's these are the default parameters. They're specified in another file called tracking parameters. These are all the default parameters. I'd advise you not to change them here. If you want to do something different, what the code does is that it first creates this file inside the same folder that you told it to work. It's going to create this file, and here these are the default parameters. So if you change them here, say you want to change for instance processing min fiber length, this is like the below this length is going to reject them. If it finds like 3 or 4 centroids that look like they're a fiber but they're less than 10, it's not going to think it's a fiber. So you can change that to 20 or to 5, whichever. You like it might depend on what you're doing exactly. But if you change them here, it doesn't change the default values in the code, but the next time you run it, the code's going to look for this file, and if it sees it, it's going to read the parameters from there instead of going with the default ones. So you don't need to, because if you start changing the default ones, you're going to forget what the original ones were, and you might... Also, this is a way of keeping track of what parameters you use for this data set, because it stays there. And if you use a different parameter for another data set, this one's not changed. So it's a simple way of keeping track of things. So here, it takes a little while. One of the things it does, I call it dilation radius. It's for the pores and the perimeter. Usually, like we looked at it when we were doing the insect dictionary. The fibers that are very close to the pores, there's a lot of confusion there because there's a little white halo around the pores.
Yeah.
So what I do is that I use the pore regions and I expand them a little bit. I dilate them.
So it rejects the fiber close to the pore.
Yeah, that's it. So like it's by less than a diameter of a fiber. This radius is 5 and the fibers are like 10.
So yeah.
So if it's a real fiber, it's not going to be completely deleted.
Yeah.
It'll preserve it. But most of the halo, if the machine learning still thinks there's fibers there, but it's not real, it's going to get rid of most of the mistakes. And the same principle for the perimeter. There's not much fibers on, like it's rare that the fiber is really against perimeter, so I give it a little more here. The rest of them, you probably won't ever have to change them, but you can go and look in the code what you do exactly. Okay, so now it's the dilation. It takes a little while, but it only does it once. Like if the file is already on the disk, it won't have to do it again next time.
Okay. So now we start the traction, or we wait for the preview and later we're gonna continue?
Well, now we started the extraction, the tracking, but we set it this parallel held to false.
Yeah.
Inside extraction point, this is the first function. So it's going to use one CPU at a time, so it takes a long time. And also, I told it to plot this initial and results. So we're not going to leave it like this for it to run. It's this is just a trial run.
Okay.
I'll show you what it does. Okay, I'm going to pause it for now. It might take like 5 or 6 minutes.
Okay.
Okay, so now it finished doing the dilation. That took like 3 minutes. It finished loading essentially after, what's this, a bit over 5 minutes.
Yeah.
Now it's starting the watershed transform. That's what I explained in the paper, was one of the first initial steps. And it's, since it's, the parallel is set to false, that's it. So it's only used in one process, called main process. But once you set it to true, it'll use as many processes as there are cores on your machine, as there are threads actually. So these are the outputs that it makes. Yeah, this one I should remove. It's not really useful. So, well, your data is fairly clean, but sometimes it gets worse than this. So this, first it looks for a separate, like all the connected regions, all the regions that are like, for each region it's gonna give it a number, and for each region that's not connected to each other, like every single connected region by itself. And then for those, it's gonna check if they are convex. So I explain all this in the paper. Like those that are roundish or oval or something, they're convex, and the ones that are a little bit like they have they go like they have like an H shape or something like that. They're a bit concave. It's gonna detect those and it's gonna split them again with the watershed function. So the objective of this is well, actually I'm showing you the result here, but if I go to the previous one. Here, this is what it found just by, this is the output of the machine learning, and it found that this region was not convex. So from there, which one is it? Boom. From there, it divided them again. So every single one of those, sometimes it doesn't work, like if it's a very small region or it's, your data, there's not many that are touching, so because the idea is for each one of these I'm going to assign one centroid, so just one, it's like the center of mass, and if the region is not convex, here there are clearly two fibers, but it would have found just one centroid. So I want to find two centroids, so that's how we split them, and here it's probably going to work well. So you see that it's there's nothing strange here where the data is most of the data is good. There's a few fibers missing here. I didn't notice that. But this is the first slice, so it's often not very a good representative. If we close these fibers, it'll go to the next one. We'll see how it performs for a few. Because when we did the example file when InSeg made the example segmentation, like a sample one, it was right in the middle, like slice 450 or something, and it looks super clean, so I'm not worried, but I'll see if the next one does it a little bit better. It probably won't make a difference for just one slice, but just to show you an example. Might take a second or two. Let me pause it again. Okay, there it goes. Yeah, there's not much difference. Anyway, I'm not really worried. One thing you can do if you really want to, I call it manual range. If you uncomment this, you can tell it to go only for a few slices, like wherever. Like I can go to 100 to 105. And then run it again. But this is just for like troubleshooting or something. Here it's just to make you an example to show you that the fibers are really found. So now it'll be faster than before because it doesn't have to dilate the volumes again. I can show you where it put them. Like this one. This file is it's a combination of both the pores and the perimeter after dilation. So if you see in the preview, the pore volumes are a little bit bigger.
Okay.
And also you remember the first slice of the perimeter was a little bit messed up, but that doesn't really matter. Because it's only one slice. You see, it says, found on disk at correct exclusive zone and dilation parameters. Oh yeah, that's also something I didn't explain. If you like, if there's a reason that you don't want your entire file, like the default parameter is exclusion zone of none, that means they will use the entire data set like it says here. But if you, for some reason, you just want some values of X, some values of Y, and a few, like you can specify whichever you want. So if you do this, it'll only work on these coordinates.
Okay.
So that's it can be useful sometimes. Okay, you see now, this is more in the center. It's slice 100, and now it's clean. Now all the fibers are there. There's no worries. So we can forget about the first few. It's often that it doesn't, because the scan properties are a little bit different, so it confuses the machine learning a bit. Okay, so now we're happy that the parameters are good. So we're going to return parallel handle to true, so it does it faster. And we have to remember not to plot anything, because it's going to stop the processing at every time it makes a figure. And also manual range, we don't use that for the. Well, you could if you wanted. You can run. You can do an entire run with manual range, but it's this is more for debugging. Like if you want to do like this was just a quick and dirty way to just do the slice 100. But if you really want to only use a few slices, it's better to use the exclusive zone, because then it's implemented in the same way for the entire process.
Yeah.
So this is. So now no exclusive zone, no manual range, all of these are false and this true. Okay, so now I'm satisfied that the first operation worked well. After the extraction, then it goes to the tracking, and then there's a lot of other steps, assignment, and then post-processing, and it does that whole procedure. It does it for permutation 1, 2, 3, then 1, 3, 2, then 3, 2, 1, and then it combines all of that, and it does a post-processing again, but you don't need to know all that. Usually, I've tested this on like 40 different data sets, and I think I worked out most of the bugs. Like it shouldn't crash. There might be a reason, like the extraction is not optimal. You may need to play with the parameters a bit, but the default parameters, they work fairly well for most situations.
Okay.
One thing that might be important, we almost always use carbon fibers, so there shouldn't be it's not really important, but the code, it doesn't know what it's looking at. Like if it's glass fibers, for instance, the diameter is bigger. I think they're around 12 to 15 microns. So it would be there's a few checks that it requires knowing the fiber diameter. So you can change it here.
Okay.
And inside the tracking params.json,
Mm-hmm.
you can change it to wherever it is here. This is in microns, and it'll work. It's a fairly minor effect, but it's better to be aware that this thing exists. And
Mm-hmm.
most of these parameters you won't ever have to touch them. So
Okay.
I won't go into detail what every single thing does. Okay, so what else? I think we've covered most of it.
So after this step, it's gonna take a long time. Like,
Yeah, it's for this scan. I think it took like 7 or 8 hours last time I used it.
okay, okay. So, like, what should be what will be output of this scan? Do you have some files to show us?
Yes. So once the extraction completes, these are the files that are going to be produced. If you open property maps with ParaView, you can already get a rendering of basically the fibers themselves. And depending on which field you select, you can either color them by length, well, by deviation here, or by length. Now, if you want to get the rendering that I made in the paper, there's a way to do that. Basically, you go into the code, the file name crop_tiff, and you have to give it two paths. First, the path we're working at, where the property maps file was generated here, and the previous folder where we had the output of the pre-processing, so it finds the original data. That's just for rendering purposes. Now, when you give it those two, also there's the renderings are going to be nicer if you crop a rectangular region inside the specimen. So the way to get those coordinates for what I call the cropped zone, you can open the file in, say, any of these files will do, really, but just so that it's nice and easy to understand, you can open, for instance, vhist in GIMP, and you select, this is a volumetric TIFF file, so it's a stack of images. If you just choose the first one, so basically on the lower left side here you have the pixel values where you're pointing at, so it's an easy way to find pixel values. So say if I go, what I had as an example was 200 by 200 here, and the lower right hand side corner is 800 by 800, so basically we're selecting this region. So that's what I have here, x values from 200 to 800, same for y values, and all of the z values. So you basically launch the script, and it's gonna import all the data that was produced by the tracking. It's gonna crop it to to these coordinates. You can also leave it to none if you want the entire zone, but the rendering is nicer, like I said, if it's nice and square. So we're going to give it a few minutes to run, and it's going to make a folder with all of the output. So first it generates these figures just to give you a notion of what it's cropped. So here you can check if your coordinates are valid. So you close all of these. Okay, once the crop_tiff script is done, what you get is a new folder called cropped results, and inside here you have all these volumes that have been cropped. And if you open this file with ParaView, this is a ParaView state file. It takes a little while, but you'll essentially get the rendering that you saw in the graphical abstract for the paper. This is also a reason for cropping. It's going to make this visualization a bit lighter to load and to handle. Okay, so here we have it. So here was the raw data, just with a color map that makes it a bit easier to appreciate that there are pores and fibers. On the bottom in yellow are the fibers, and in blue and cyan are the pores. And the two big ones are the fibers, the individual fibers colored by their angle, their deviation from the vertical, and on the right hand side, the fibers colored by the length. So you can play with the, essentially all these elements are individual. You can turn them on and off as you like, and you can select, like by playing with the opacity, you can decide you want to show only the fibers, like here, only the fibers above, say 35 are shown, the rest are completely transparent, so you keep only those. Or you can decide you want to show only the fibers that are very aligned, so you keep like those towards the low end of the range. This. So here you have mainly the very straight fibers, and you can also tell already that it's the longer fibers are going to be more in line with the extrusion direction. Now the same thing for the lengths. You can go and select the other field, this one, and you can change the opacity characteristics to show, for instance, only the short fibers or only the longer ones. So it becomes a lot easier to understand your microstructure this way. Once you have this processed, you can use a script called fiber statistics. You tell it, for instance, in this path, I think it'll work. It's just going to process it's going to look at all the fibers that I found. It's going to do a few, actually the plots that I make in the paper. So it gives you the average length here. Boom. So you can see these are the plots I made in the paper. Like the correlated length and deviation. You have the cumulative distribution function for both variables. These histograms.
Those results you can present.
Yeah, that's pretty. It's a nice way to interpret your data. And also, I think it saves them. These files are automatically saved.
Mm-hmm.
Did I? Yeah.
Okay.
Yeah, and here you have a little file with the statistics. So mean length, the standard deviation, the standard error, mean deviation. Deviation is for angle, like division from the vertical. 23. How many fibers are?
Yep.
There's more, but this is what was included in the public Git version. At one point I will do an update with my latest development.
Okay. So basically that's it, the step is done.
Excuse me?
Basically it is done, right? It's finished.
Done. This is once it's done. The one I didn't launch it now, but once you process the entire thing, you're gonna get this property maps. Actually, I'm not. It doesn't. It was just property maps in the one I put in the public version, but you can basically reproduce the figures I made in the paper.
Okay.
that's it.
Okay, thank you very much for the tutorial.
Yeah, have fun.
Yeah, I'm sure it's gonna be really efficient for people and it's gonna help lots of people.
Hopefully people use it for a whole lot of different things.
Yeah, don't worry. So yeah.